All right, hi everybody. Welcome back to another Physics 2 video. This one we're going to look at electric force field and potential. Okay, so let's jump right in. Okay, so here they give us a picture of two spheres. We can see that one has a larger radius than the other. They tell us two conducting spheres connected by a conducting wire, as shown in the figure, are at rest on an insulating table. Sphere 1 has a larger radius than 2. Both spheres have a net positive charge, but the magnitude of the charge in each sphere is unknown. Okay, so before we even get into that, let's just break some of those things down. What do we know? They're conducting spheres. That means that electrons are allowed to move around freely between the spheres. So if one had more, a greater concentration of charges in it, they'd be able to spread out and go to the other sphere, right? And why would that be? Because they're connected by this wire. So the wire's conducting, the spheres are conducting. Electrons can flow between the two spheres through that wire, okay? It's on an insulating table. That means that our charges are conserved within these two spheres. None of the charges can leave these spheres. So if you have a total of, let's say 5 coulombs of charge, no matter where these electrons move around, at the end of all that motion, when they reach equilibrium, you're still going to have the same net charge. You'll still have that 5 coulombs in total. All right, so that makes sense to us. Let's read the question. A student wants to investigate whether the magnitude of charge on each sphere is different. Measurement of which of the following information is useful for this purpose. So let's first see if we can answer that question. Do the two spheres have a different amount of charge? Okay, so I'm just going to draw my picture of these over here. My large sphere, my smaller sphere, and they're connected. Now, what's inside these spheres? We have a whole bunch of positives, right? And negatives. But who's winning out? The positives are winning out. But the negatives are the things that are allowed to move around. Okay. So if we've reached a state of equilibrium, what does it mean to us? It means that those negatives are now equally pushing off of each other, and they're spaced evenly throughout that conductor, right? So let's think about that. Let's draw that. Representation. Obviously, I'm not going to be able to draw all the electrons, but I'll just put some negatives in here to try and represent that spacing. Okay, so as I draw these, I'm trying and keep them somewhat uniformly spaced. Maybe there's even one here. So as I put my negatives in, you can see that for the most part, all those negatives have the same space around them. They're pushing equally on each other. Like this one feels a force because of those electrons around it. And this one feels that same amount of force. So just by doing this type of drawing and diagram, we can really reason that there's more charges within here than there are in here. Right? What you have to remember is there's actually more positives in here as well, right? So throughout here, we also have a whole bunch of positives. And the same thing in the wire, and the same thing in this sphere. So for the most part, the charge density is constant throughout this system. That's what it means for these electrons to come to a state of equilibrium. It doesn't mean that the absolute number of electrons on the left and on the right is the same. Usually we see this a lot when we have equal sized spheres, right? If these spheres are equal and we know that there's a net charge of those 5 coulombs, like I said before, well, that would mean that there's 2.5 coulombs here and 2.5 coulombs here. Well, that's no longer the case when we have unequal sized spheres, right? Well, what's going to happen? Which sphere is going to have more charge? Okay. If you think through this a little bit further, you should be able to see that once we've reached equilibrium, the electrons are no longer flowing. Okay, so that's going to help us as we read through these. Choice A tells us the potential difference between the spheres is something that would tell us if there's more or less charge on them. Well, is that true? Is there any potential difference? There's actually not. There's no potential difference because if there was, the electrons would be flowing. They're not flowing. They've reached that steady state, that equilibrium. So since they're not flowing, we know there's no potential difference. There's no potential difference in either case. No potential difference here. No potential difference here. Okay? That potential difference is going to be caused by an unbalanced concentration of charges. Okay? So choice A is out. Let's scroll down a little bit more and think about some of these other choices. Could we measure the current between the two spheres? And if there's current, then there must, because a current must exist between two objects with different amount of charge. Well, we just proved that that's not true. There is no current. We've reached a steady state, but we do see that there's this unbalance of charge here. Okay? So that's not going to help us to see how much charge is on the larger as compared to the small. Let's see. The attractive force between a magnet and each sphere, because different magnetic forces are exerted by objects with different charge. Do magnets interact with charge? Only moving charges, right? So moving charges create their own magnetic field, which then in turn can interact with those, if you have a wire with current in it and there's current is moving charges and that's in a magnetic field, that's going to feel a force. But these just sitting here on the table, that doesn't seem like the best option. Maybe you could devise an experiment where you're dropping this, you detach them from each other and you drop the spheres and you put them in a magnetic field and see how much force there, is applied to them. It's a possibility, but doesn't seem like they're telling us anything about getting these spheres moving. I don't think it's a good choice. Let's look at choice D. The attractive force between an uncharged metal block and each sphere. Because different electric forces are exerted by objects with different charges. Well, we do know that there is a relationship between the charge on something and how much force it applies. So here's the equation we use for electrostatic force. K, Q1, Q2 over R squared, where Q1 and Q2 are the charges of our two objects. Now, I want to read that again and point out a couple things that people, that confuse a little people. So this says between an uncharged metal block. So here's our block. And a lot of people would say, hey, if this is uncharged, it's going to have a net charge of 0 coulombs. It's uncharged, which means I'm going to draw all of my positives. They're in a solid, so they're stuck in place. And actually, I'm not going to use color for my negatives. I'm going to draw them in pencil because in a second, I'm going to move them. But we know that they're balanced out right now because our net charge is 0. So why would this, if 0 goes in here, why are we going to feel a force? You should look this up. This is, find a quick YouTube video somewhere. If you put an aluminum can on a table, aluminum can has no charge, and you bring a balloon nearby and you rub that balloon on a piece of wool or fur or even your hair, you get those negative charges built up in the balloon. As you bring it close to this aluminum can, there will be an attraction here. Why are they attracted when we're saying this is 0 charge? Shouldn't the 0 go in here? And it has to do with the fact that when you bring something close by that has, in our case, our spheres are positive, what happens if this is conducting? It allows the electrons that are inside of here to move close to that edge where we have a charged object. So now if we just kind of look at this half, we see there's some attraction happening here. This block is being pulled towards this positive charge here. So there will be attraction between charged objects and neutral objects, okay? So since the block is the same in both cases, this Q2 will be the same both times, but if we substitute in the larger sphere, that will be Q1 and we'll get a force. And then we try the experiment again, Q2 stays the same because it's the same block, and the smaller sphere would be a different Q1, and the student would measure two different forces between that block and the spheres, and he would say, hey, the only thing I've changed is these spheres, which means they must have different amounts of charge on them. So hope that one helped. It's an interesting problem, has a lot of good electrostatics in there. So see you in the next video, and good luck. Take care.